Hi students, I welcome you to the online lecture series on linear integrated circuits. Uh, in this session, we are going to see the basic concepts and definitions related to this LIC course. So here, the predominantly with that we are going to read about operational amplifier, the gain, and after that we need to know what is a differential amplifier, what does common mode rejection ratio mean, and what are the some of the terminologies associated with this op amp, that is something like input offset voltage, slew rate, what is frequency response, what is bandwidth, what is negative feedback, and what are the advantages of the negative feedback. In these basic concepts, you have already studied the concepts, some concepts such as gain, differential amplifier, CMRR, frequency response, bandwidth, negative feedback, etc. already in the previous semester. And in this semester, before starting the syllabus, I'll be giving you a short explanation about op amp. Okay, so now let us have a short, very short overview of what an differential amplifier is and what are the significance of this differential amplifier. So the basic function of a differential amplifier is to amplify the difference between two signals. So basically what it does is it can amplify the difference between the voltage levels in two different signals. So this is the simple block diagram of a differential amplifier. So here V1 is one signal, V2 is another signal with respect to ground, and this is the difference between V1 and V2. V out, as per definition, V out is proportional to the difference, that is proportional to VD. So this diagram shows BJT based differential amplifier. Here VS1 and VS2 represents two different signals, and these are emitter coupled BJT pair, and output is taken across the collector of of these two BJT amplifiers. So as I told you before, V0 is proportional to the difference between V1 and V2. So when we convert this proportionality into equals, so here we get a constant of proportionality, which is AD. So AD is called as the differential gain. AD is the differential gain of the differential amplifier. So next, what is common mode? So even though this, as per definition, this differential amplifier need to amplify only the difference between these two signals, but in general the output V naught, it has an additional component which is AC into VC. This is called as a common mode gain. AC is called as a common mode gain. So what is common mode gain? So when we consider two different signals given as input to the amplifier, at some point of time, these being the signals or time variant signals, so at some point of time both the signals will have a common value, equal value. So at that time the output of the signal, output of the differential amplifier will be the average of the two signals, that is V1 plus V2 divided by 2. So actually this is not required by the designer. This is not required as per the design. So there is a need to remove the common mode signal. So that is where this concept of common mode rejection ratio comes in. So CMRR is defined as a ratio of differential voltage gain to the common mode gain. So AD by AC. When we convert this into a log scale, it will be converted to 20 log of 20 log of modulus of AD by AC. So whenever the common mode gain goes less, the value of CMRR will be very high. So as per design, it is very desirable that the common mode rejection ratio is very high for any differential amplifier that you are using. The next, moving over to the application of the differential amplifier, it has two different modes of operation. One is called as common mode, the other one is called as differential mode of operation. In common mode, we considered that the difference in voltage is zero, or in other words, the inputs V1 and V2 are same. And in another mode of operation is called as differential mode, where this V1 and V2, the two signals given to the differential amplifier, are opposite to each other. When one signal is minus Vd by 2, the other signal will be plus Vd by 2. You have already derived the gain expression for gain of differential amplifier in the previous semesters, and I hope I think you should all go and refresh your knowledge on this topic once again. So why is differential amplifier very popular? So when we have this common mode rejection ratio very high, the circuit is less sensitive to noise. That is, the circuit is becomes almost immune to noise, so that you will have reliable amplification. And what, what is the significance of CMRR? So the major goal, since your differential amplifiers or semiconductor based devices, they are prone to environmental induced noises such as temperature based noises, thermal noises, electromagnetic noises, etc. So it is very significant that the noise should be removed. Next, what are the different configuration of differential amplifiers? Basically, we have four configurations, that is dual input, balanced output. Number two, dual input, unbalanced output. The third, single input, balanced output. And the last is single input and unbalanced output. So most widely used configuration is dual input, balanced output differential amplifier. This is the diagram of dual input balanced output differential amplifier. So this is the most widely used configuration. So if you look here, here you have two intercoupled BJT. So as you have already seen, signal 1 and signal 2, and the output is taken across this collector. Just you seeing these different circuit, you just remember the changes in these circuits. So here the output is taken across these two collectors. Here if you see the unbalanced output, you will have the output taken across any one of the legs of the collector with respect to the ground. So single input balanced output means you will have any input on any one side of the on any one base, and the output is taken across two collectors. On the other hand, single input unbalanced output means you will have only one input, and the output is taken from one leg of the collector with respect to the ground. So next, one more important topic that you have to study is about current mirrors. So what is basically a current mirror? Is it is a circuit that is used to maintain a constant current source. In other words, it is a circuit that can output constant current that is equal to another reference current. What is the need for this current mirror circuit is, in analog electronics you would have studied about the various biasing circuits, that is a voltage divider bias, emitter coupled bias, emitter to base feedback bias, etc. Also, while studying those biasing circuits, you'd have studied uh, factor such as stability factor, S dash and S double dash. Basically, these biasing circuits are variable, and they change the bias points, that is the Q point may change in position across the load line due to the change in the biasing levels. So due to this, there is a need for a constant current source. So that is where this constant current sources or current mirror circuits come in. So one of the most important current sources circuits are Whitlar and Wilson current sources, and you can go through this in the textbook of analog electronic circuits. So the next topic is the frequency response. This particular graph shows the frequency in hertz from 20 hertz to 20,000 hertz, which is the hearing frequency window of the human ear. And this y-axis shows the sound intensity in dB levels. Okay, so if you see this graph, the human hearing is very sensitive to the voices in around 3000 hertz. Around 3000 hertz, this human ear sensitivity is very high. So if you look at this graph, you can see that the human ear is very sensitive to the frequency in 3000 kilohertz. Sorry, 3 kilohertz. So which happens to be the frequency of the voice of a child. And as the frequency increases, we can see that we are less sensitive to the frequencies below and after 3000 hertz, and so we can hear the noise or voices at 100 hertz when the intensity goes above 20 decibels only. So what is the need to know about this graph actually? For example, if you are designing a audio system, so you have to tune your amplifier such that it can reliably amplify the signals in this hearing bandwidth of the human ear. And one more important point is that you need to amplify not only the signals, but also you have to have in mind the sound intensity level, because when you increase the sound intensity level, it increases across the whole spectrum, and so that it does not any frequency component must not go above this discomfort threshold. So it is why it is important to know about the bandwidth and the frequency response of these amplifiers. So that's all for this session, guys, and in the next session we'll be going through the basics of linear integrated circuits, where I'll be covering the basic information about op amps, ideal op amps, general op amp stages. Okay, and in the next session after that, I'll be covering the internal circuit diagram of IC741, followed by DC and AC performance characteristics. Okay, thank you.